Hi, this is a quick video about the bioelectrochemistry of the total purine sensor from Zimmer and Peacock. So the first thing to say is this is what the sensor itself looks like. It's a object very similar to a glucose strip. It's 7 millimeters by about 25 millimeters, and on it we have a sensing electrode which consists of 3 enzymes: adenosine deaminase, purine nucleoside phosphorylase, and xanthine oxidase. Now what these enzymes mean is if the sample natively contains adenosine, then adenosine is converted by the adenosine deaminase into inosine. Similarly, if inosine is converted from adenosine, or importantly is just natively in the sample, the inosine is converted by the purine nucleoside phosphorylase into xanthine, and we have a phosphorylated sugar. And at the same time, then xanthine is converted from adenosine to inosine, and then into xanthine, or inosine is converted into xanthine. If there's xanthine natively in the sample or as a result of the upstream enzyme cascade, then the xanthine is converted into urate. So what this means is that we are able with this purine sensor to directly detect adenosine, directly able to detect inosine, and able to directly detect xanthine. And therefore the signal that we have on the website today, the total purine signal, is equal to adenosine plus inosine plus xanthine. Now what is possible, so we do have a stack of microfluidic technologies and multiplexing capabilities. So this is what is possible rather than what we have on the website today. But what is possible is to construct a multiplexed biosensor cartridge such as the one I've shown here, where you have a sample placed here. So for example, I mean, it could be 50 microliters, it could actually be less than that, but for example 50 microliters, which is a sort of drop of blood. The microfluidic channels take the sample down to these individual electrodes. In this case we only need 6, but in each I'm going to say well in a minute, but what we do is you put a sensor there. So for example in that position there, and for example there you can put the total purine sensor, which is sensitive to the sum of adenosine plus inosine plus xanthine. Now what we can then do is start to deconvolute how much of the sample actually has adenosine, inosine and xanthine in it, and with the deconvolution is like this. So if we call that sensor 1, we can have another sensor in this position 2, let's say, which is only functionalized to be able to detect inosine plus xanthine, and so we can call that sensor 2. And then in maybe we call it position 3, we have another sensor that's functionalized only to be able to detect xanthine, and we can call that sensor 3. So what this means now is that we've got 3 sensors all receiving the same sample, because the sample is split in the microfluidic device. It wicks down and what's called capillary action into the 3 sensing zones, and in each sensing zone we have a different sensor with slightly different functionalities on it. And so when we measure this signal from sensor 3, which is in location 3, we have xanthine. When we measure the signal in sensor 2, what we actually have is the sum of inosine plus xanthine. So therefore, if we want to know the signal for inosine, we just take the difference between S2 and S3, and that will give us the deconvoluted signal or contribution from inosine. And then if we want to know deconvolute the proportion of the signal from adenosine, then we take the signal from S1, which is the total purines, and we subtract the sum of the signal from sensor 2 plus sensor 3, and then we can do adenosine. So what we have today is the total purine sensor, which is basically measuring the sum of adenosine, inosine and xanthine, and it is harder to deconvolute each individual contribution from there. But once you start going to a multiplexing, then you are able to start deconvoluting the contribution of the different purines, let's say, or the concentrations of these different purines in the sample. Okay, I hope that helps.